behind the scenes what is happening is there is pre-compiled C code, implicit element by element behavior of operations. Let's see, now we have 4 dimensions. Now a lot of people get confused between np.empty and np.random. So here I have a Boolean array split after the third and the fourth column. So even when you're slicing and you think that you've created a new array, it is pointing to the same thing in the memory. It got converted to just one D array. In the previous videos, a lot of you have been asking that how do I get started with new libraries, new tools, new packages? Because I know a lot of you are getting started with machine learning. Although these are very basics, I know you're wondering how did we get started, right? So let me tell you over here. Almost all good tools, packages, libraries are going to have awesome documentation. Now I understand that going through the documentation can be a bit slow and boring for most of you, and that is how you can leverage these tutorials. So if you go through any of my machine learning tutorials, I always refer to the documentation, the examples that they have given. I write code and explain it to you as well, right? So what you can do over here is 2 things. So you have 2 options. First thing that you can do is go through the entire tutorial once. So I'll be going through the documentation. You will have an idea that what am I doing. And then the link to the code is in the description. So you can open it parallelly like this, go through the code and try writing it yourself. The second thing that you can do is open the tutorial itself in one tab and try writing the code parallelly as you watch the tutorial. So you can do any of the 2 things, but I highly recommend that you should try writing the code yourself so that you become very comfortable with it. You will feel a lot more confident. So leverage the tutorials, but make sure that you try writing the code so that you are completely confident that yeah, you understand these things. It is not really that hard. I am not asking you to mark up these syntaxes. Nobody has to mark up. You just should know that okay, these are the things supported, these are the things that are possible, and at any time whatever is needed, you can just refer to the documentation and you can quickly sort it out, right? And when you do end-to-end projects, you'll be writing the same code again and again so many times that you'll get used to it. This is true for any language, any tool, any library. Don't try mugging up syntaxes. In fact, just try writing code, try building a lot of projects, and you will get used to the syntaxes. And over the time, they will start coming naturally to you. Before we move ahead, I would like to congratulate you for taking a step towards learning ML/AI. I truly believe that all software engineers will eventually, sooner or later, jump into ML/AI. They will upskill. It's just a matter of time. And that is why I'm also creating this free playlist covering all the topics, creating so many videos one by one. But I'm also teaching live. I am taking a 7 weeks live hands-on generative AI course. So hands-on meaning we'll be covering 10 small and big projects. You can check out the curriculum. I absolutely love hands-on courses because we get real project experience over there. The last hands-on course got such great feedback. You can in fact check testimonials of all our Educosys courses over here. And I hope if you're interested, you will check out all the details and enroll. I'm really proud of everything that we are doing, and I am really excited to see you over there. But for now, let's continue. Let's start with absolute basics of NumPy. NumPy stands for Numerical Python. It is an open source Python library widely used, contains multi-dimensional array data structures such as homogeneous ND array. Now, first things first, what is homogeneous? Now, when we have arrays, all the elements in the array are going to be of the same data type, like integers, floats, or strings. Now, one interesting question for you. In real cases, when we have real data, you must have seen Excel's CSVs, the data is not going to be of the same type, right? Like for example, if you have housing data, then you must have some things as strings, something as integers, some things as floats, right? So there can be different types of data. So if I want to store different heterogeneous data, especially over the columns, right? So suppose one column is of integer values, one column is of the float values, one column of the string values, what library can I use? Hint is that it is built on top of NumPy. It is very widely used. We have already covered it in the machine learning playlist. It is an extremely important library. Let me know in the comments. I want to know how many of you are following it and understanding these little things. Okay, very, very important concepts. Now let's continue. Large library of functions that operate efficiently on these data structures. Now let's quickly go through what is NumPy and okay, the details of it. But okay, before that, to give you slight confidence, let's start with our first example code. Okay, so if you want to know how to install NumPy, we can just go over here. We can do pip install NumPy. I'm using Jupyter Notebook. You can set up Jupyter Notebook, right? So I'm just doing Shift Enter to run it, and we have installed NumPy. And I'm going to go back and I'm going to import NumPy as NP. This is the most common alias that is used, so we'll use the same thing. So we have imported NumPy as NP, and we are going to copy this. This is going to be our first code. So you can see that as they're giving this, it is code, right? So I can just copy it like this and I can just paste it, right? So very simple. If I do this, it is giving me shape. What is shape? The number of rows and the number of columns. So here you can see the number of rows is 2 and the number of columns is 3. It is there in the documentation ahead, but this is the first example code. So this is just to get some confidence that, okay, we are able to install it, import it, and we are able to write some code. Now let's go through the basics. What is NumPy and some interesting concepts. One question that should be coming to your mind is that why do we need NumPy arrays? Why can't we just use Python lists? So for that, it is very important to understand the differences between NumPy arrays and standard Python sequences. Now, trust me guys, if you can just listen to me for the next 5 minutes, this is the only theory that you need to understand, that why do we need NumPy, and after this we will just be writing code. I have gone through a lot of YouTube tutorials that are there on NumPy. No one covers it in so much detail and it is given so beautifully in the documentation. So please listen to me for next 5 minutes and a lot of your concepts will be so clear. It's just absolutely beautiful. Okay, just 5 minutes dedicated attention, you can do this. Okay. So let's start with the most important point first. See, NumPy arrays facilitate advanced mathematical and other types of operations on large numbers of data. So whenever we have advanced mathematical and other types of operations on large numbers of data, such operations are executed more efficiently with less code in NumPy arrays, using NumPy arrays, than is possible using Python's built-in sequences. Now, why is that the case also? We'll go through it, that why is NumPy fast, and they've explained it very beautifully through an example. So let's go through the example first. So what they are saying is they have taken two 1D sequences A and B, and they are finding another array C where they are finding A of I into B of I, and they're just saving all the values in C. Okay, so it's obviously another sequence is going to be of the same length. Okay, and the problem is that if A and B contains millions of numbers, okay, so if it becomes huge, then we will have to pay the price for inefficiencies of looping in Python. So looping is not efficient in Python. This is not going to be efficient, but the same task could have been done a lot more quickly in C. Okay, so they've given us the C code also. Right now they're not talking about NumPy. They're saying, see, in Python we can write like this, but this will not be efficient if we have millions of numbers. In C, it would be a lot more efficient. So they have given the code in the C language also. So Python and C. Now what happens when we write the code in C? We save the overhead involved in interpreting the Python code and manipulating the Python objects, right? But what is the con over here? The expense of benefits gained from coding in Python. So the code actually in Python is easier to write, especially when the dimensions of the arrays increases. So if there is increase in the dimensionality of our data, like suppose it becomes 2D array, then we will have to write like a nested for loop, right? So the C code is not very easy to write. That's why a lot of people struggle when they switch from Python to C, because they are used to writing Pythonic code, right? So what NumPy does is it gives us the best of both worlds. So in Python, there are inefficiencies of looping. In C, writing the code is a bit, hard. So NumPy gives us the best of both worlds. So what happens is element by element operations are the default mode when an ND array is involved. What is ND array? So if you go up, at the core of NumPy package is the ND array object. Okay, this encapsulates the n-dimensional arrays of homogeneous data types that we had talked about, right? So this is the default mode, element by element, right? So the element by element operation is speedily executed by pre-compiled C code. This is so important for you to understand that NumPy, behind the scenes, what is happening is there is pre-compiled C code, and that is why it is more efficient than writing Python lists, right? You could actually write the same code in Python, but it would not be so efficient. NumPy, behind the scenes, there is pre-compiled C code. Very, very important. So easy to write. You just do C equal to A into B, and it will take element by element. It will find A of I, it will find B of I. Behind the scenes, when you write C equal to A into B, you can imagine that in Python this is happening, or in C this is happening. So there is essentially a for loop that is written for you. Okay. So this is what the earlier examples do at near C speed. So you have the benefit of the C speed, right? But the code simplicity we expect from something based on Python. The NumPy idiom is even simpler. This last example illustrates two of NumPy's features, which are the basis of most of its power: vectorization and broadcasting. So it is very important for us to understand what is vectorization and what is broadcasting. Let's do that. So, but the basic thing that you should remember for now is NumPys are more efficient whenever it comes to performing mathematical and other types of operations on large numbers of data, because behind the scenes there is pre-compiled C code. So it is giving us the benefit of both worlds. It does element by element operations by default because it is using ND array. Okay. Now let's understand what is vectorization and what is broadcasting. Starting with vectorization. Vectorization describes the absence of any explicit looping and indexing. So here, did we write any loop? No, right? So we did not have to write any explicit for loop. So we don't need any explicit for loop. We don't need any indexing. Am I doing A of I, B of I? No, it's just equal to A into B. So very easy, right? Because behind the scenes, there is optimized pre-compiled C code. Let's quickly go through the advantages. You have already understood it. Let's just quickly go through it. It is obviously concise, easier to read. Fewer lines means fewer bugs. Code more closely resembles a standard mathematical notation, right? Obviously, C equal to A into B seems very easy, right? Vectorization results in more Pythonic code, as I had already said. Without vectorization, our code would be littered with inefficient and difficult to read for loops. I have written the code in C++ for the longest time, so I slightly disagree over here. Let me know in the comments. This is typical Python versus C++ mentality. Python people usually find it very hard to read the for loops. Anyway, you get the point that it is easier to read and write, yeah? Now, broadcasting is the term that is used to describe implicit element by element behavior of operations. So you already know that by default there is element by element behavior, because the default mode when ND array is used is element by element operation only, right? But the term that is used is called broadcasting. It makes sense also. Broadcasting is like you are broadcasting the same thing over all the elements, right? So you sort of understand what it means. And it is not true just for arithmetic operations, but for logical, bitwise, any functional operations, implicitly it will do element by element. Okay, and we'll actually write code and understand. So that is why going through the basics, the theory will really help you, because when we write code, you will understand that why is it able to do it behind the scenes, right? And how it would be doing. Now you have a clearer idea. And here they have mentioned that A and B could actually be multidimensional arrays also. And they don't even have to be of the same shape. Same shape meaning the number of rows and the number of columns don't even have to be same. Now that is very interesting. When we write code for this, you will understand this better. So when we have arrays with different shapes also, what happens is whatever is the smaller array that expands. So for example, we have 2 by 2 and 3 by 3, just giving you a slight example. You can add some extra elements to add that one row and one column, right? So now that will implicitly get converted to 3 into 3, or you can imagine that, okay, now this 2 by 2 became 3 by 3, and then the operations will happen element wise, right? So under the hood, it will take care of all of these things. We don't even have to do it, right? In such a way that the resulting broadcast is unambiguous. We'll go through it. We'll go through the rules of broadcasting. Don't worry about it. How it happens, we'll go through it. Don't worry, right? Now just coming through this, you can read about it more. See, ND array is a class possessing numerous methods and attributes. Many of its methods are mirrored by functions in the outermost NumPy namespace, allowing the programmer to code whichever paradigm they prefer, right? This flexibility has allowed NumPy array dialect and NumPy ND array class to become de facto language of multidimensional data interchange used in Python. So you can actually use ND array a lot. A lot of people do this. It's fine if you did not understand this for now. Don't worry about it. For now, I think it's time that let's get started with writing some more code, and let's get used to the code now. Let's go back to writing our code, and if I go back, we have already installed and we have imported and written an example code. So they have talked a lot about what is an array. I assume that you all know what is an array is just a structure for storing and retrieving data. This is 1D array, this is 2D array. Now see, in NumPy the idea is generalized to an arbitrary number of dimensions. So it can be 4D, it can be 5D. That is why the name is called ND array. It basically represents n-dimensional array. And in the entire documentation, whenever they are using the term array, they are basically referring to an instance of ND array. So get your basics right. Let's go through the fundamentals quickly. So this is how you can actually create the array, and you can assign it to a variable A. So here we created the array like np.array, and we assign it to the variable A, and you printed A, you will be able to see the array, right? You can also access the elements. So here they have accessed A of 0. It is 0 index, right? So NumPy is 0 index, right? Like most of the other languages. So if I do array of say 2, and if I run this, you'll be able to get 3, because why? 0th index, first index, second index. At second index, what is the element? There is 3. Not just for accessing, I can also assign, like for example, A of 3, I want to assign to say 13. And if I run this, it has assigned the value. And now if I print the entire array, you'll be able to see 1, 2, 3, 13. So 0th index, first index, second index, third index is 13. So this is fairly simple stuff, right? Now I can also do slicing like how we do in Python. So right, slice notation also works over here. So if I do A colon 3, or let's take another example, suppose till 2, what will happen? I'll be able to get 1 and 2. And this is not just for the front elements. I can also do for the last elements. Suppose I do 3 and colon. So I will be able to get 0, 1. So 0, 1, 2. So from the third index, I'm getting 13, 5 and 6. So similarly, if I do say 4 and then this, I'll be able to get from the fourth index and so on, right? So it is not number of elements, it is index. Some people get confused, like it's not like you'll get the last 4 elements, it's from fourth index you're getting the elements, right? And you can also assign this new array to another variable. Like for example, if I assign this to B, okay, and if I run it, now like suppose I add over here, and if I print B, you'll be able to see B is what? It is an array of 1 and 2. Now once I've assigned it to B, what I can also do is I can check out, suppose what is B of 1. I'll be able to see 2, right? If I tried seeing say B of 3, I will get what? Indexes out of bounds, because there are only 2 elements. So I can just access like this, right? So this is how you can play around with it, and like it's fairly simple stuff. So if I have to show this also, I'll just copy paste it quickly. They are basically 3 rows over here, right? This basic stuff. Let's move on and let's check out the array attributes. So what are dimensions, shape, size, data type and all of this? Let's write code for this. Coming to number of dimensions, shape, size and data type, we'll take so many examples that it will be completely clear. Let's start from the example that we were considering. So if I just print number of dimensions, and if I run this, here you can see the number of dimensions that it is showing is 2. Now you must be thinking that Keerti, how is the number of dimensions 2? Let me take a lot of examples and it will be completely clear. Just stay patient with me. What I'm going to do is, firstly, I'm going to do np.array. And I'm going to pass a single value to it, okay, just 2, or I can pass anything, I can pass 23, okay, I'm passing a random value, there is no like multiple values, there are no square brackets, and now if I print this, okay, so this is the array. Now let me add a few print statements printing all of these values, so we'll be able to print for all the examples. Just give me 1 minute. See over here, the number of dimensions that we got was 0. There are absolutely no dimensions, okay. By the way, dimensions are also called axes. So here if you see, dimension of an array is something referred to as an axis, okay. So we'll talk about that a bit more, but see now here there are 0 dimensions. So the shape is empty. Why is it empty? Because shape is what? It is basically a tuple of non-negative integers that specify the number of elements along each dimension. Now, if there are no dimensions, how can you tell the number of elements along a particular dimension, right? There are no dimensions. That is why shape is empty. So the length of shape is always equal to the number of dimensions. So here you can see that they have actually done it. Length of shape is always going to be equal for the number of dimensions. And we'll see that in a lot of examples. So that should be clear. That how many dimensions are there? You are just telling the number of elements for each of those dimensions in the shape. Size is total number of elements. Here we have 1 element, so that is why size, okay. Now let's copy this and let's take more examples. Now suppose instead of this 2, 3, I just add 2 elements in like what you call one-dimensional array, right? So let's run this. Now one-dimensional array, there is number of dimensions is 1. What is the shape? The number of elements are in that particular dimension. So in this particular dimension, what are the number of elements? 2. So the length of shape, how many dimensions? 1, right? So that is why the length of shape is going to be 1. Size is total number of elements, which is 2. This should be easy to understand, right? There's nothing hard over here. If I make it 3, this should be fairly easy, right? So the shape is now 3. Why? Because there are 3 elements. The number of dimensions remains same. Now in this itself, if I have to add another dimension, how can I do that? I am going to copy this and paste it, and these two will be different elements in a new dimension, right? And if I run this, now you can see the number of dimensions is 2, right? What is the shape? See, shape is 2 by 2. You can think of it like 2 rows, 2 columns. That is how you're used to seeing, right? So this is 2 rows, 2 columns. But you can think of it like this. The number of dimensions are 2. This is one dimension ka elements. This is another dimension ka elements. Now in this particular dimension, how many elements are there? 2, right? What are the total number of elements which are there? 4. Another thing to note over here, the size will always be equal to prod of all the elements in the shape. So total number of elements are what? Over here 2 into 2. Here it was 3 into 1, 2 into 1, right? Here it was 0 only. Here it was 1 basically, size is 1. Now here the size is 4. Let me actually give you more examples, even more clearer. Let's do one thing. Let's actually add one or two elements for now. So here, do you think the number of dimensions is changing? Let me know. See, the number of dimensions is same only, just that in each dimension we have added some more elements. So in each dimension there are now 4 elements, right? So the size becomes 2 into 4, which is 8. The length of the shape is 2 because there are 2 dimensions, right? Now the number of dimensions that we took was still 2. Let's take one more example and let's try to add more number of dimensions. So what I can do is I'm going to copy this whole thing and I'm going to make this as an element in a particular dimension. So I'm going to copy and I'm going to paste it as a new element in a new dimension. So I have to add another bracket for this particular dimension. Now if I do this, you can visualize it something like this. This is just for the visualization. Now the number of dimensions is 3. How? See, the shape is 2 by 2 by 2. Now let me actually make this clearer by adding more elements. By the way, in this, let me show you something. If I remove one element from this, so if there are 3 elements in this one and 4 elements in this one, what do you think will happen? We'll get an error. What is the error that I'm getting? The requested array has an inhomogeneous shape, right? So the shape should be same. So similarly over here also, if I give this, it is going to give me error, right? So make sure that the shape of the elements are same. Now here, suppose I am adding one more element, right? So let me just do that. And now if I run, see the dimensions are 3. So this is first element and this is the second element of our first dimension. So in our first dimension, there are 2 elements, right? Now in each dimension, there are 2 by 3 elements, right? So 2 rows and 3 columns. You can think of it like that. Now suppose in this also I want to add another dimension. Suppose we want to go 4D. So what am I going to do? I'm going to copy this and we are going to, let me actually make it more beautiful. I'm going to add this as another element in this new dimension and I'm going to add another bracket over here. That's it, simple, right? And now if I run this, see now we have 4 dimensions and the number of elements in each dimension. So there are 2 elements in the first dimension. This is the first element, this is the second element. Now in each of these dimensions there are 2 by 2 by 3, right? So this is one element, this is second element. So this is these 2. Now in each of this there is 2 by 3. So this is 2, this is 3. So if you see, the last 2 are usually like rows and columns that you can understand, right? And this is somewhere given in the documentation also. This is very interesting. What they are saying is that it is a familiar practice in mathematics to refer to elements of a matrix by the row index first and the column index as second. This happens to be true for 2D arrays. But for a better mental model is to think the column index as the coming last and the row index as the second to last. So if you see, always I'm talking about the last 2 as rows and columns, right? So that's why you understand it better. This generalizes to arrays with any number of dimensions. So even if there are 5 dimensions, 6 dimensions, you will be able to understand it better. So these little things will really set you apart. By the way, 0D is called scalar usually, 1D is called vector, 2D is called matrix. We'll do a proper visualization of all of this in the upcoming video, so stay tuned for that. But anything which is like ND, right? So greater than 2D is usually called tensor. So that is why you must have heard of TensorFlow, right? Tensor is nothing but a simple ND array. Right? Very, very simple, just fancy terms that are given to it. So I hope now dimension, shape, size is completely clear. And let's actually just check out the data type as well. So now if I run this, here you can see the data type is N64. Coming to creation of basic arrays, so there are some basic arrays that we usually need to create. Let's get started with the first one, np.zeros. So as the name suggests, if we want to create an array which is filled with zeros, we can use something called np.zeros. Now in the example that they have given, they are just passing 2. And what it is doing is it is creating an array which is filled with 2 elements and both of them are 0. But if you actually do np.zeros, you can see that we can pass shape. Now there are multiple attributes that you can pass, but if I can pass shape, it doesn't just have to be 1D array, obviously, right? I can pass of any shape, any dimension. So if I pass it, by the way, I can't pass like this, 2, 3, okay? A lot of people make these mistakes because it is trying to interpret 3 as a data type. So shape is just one of the attributes that you're passing. So it is expecting the first attribute to be shape. So you have to put this in another bracket. Now this entire thing is shape. So what you will generate now is a 2 by 3 array which is filled with zeros. Now if I want to increase the dimension, I can obviously do that as well. I can make this 2 by 3 by 7. So now you can see there should be no confusion over here. There are 2 elements. So 2 elements for the first dimension and 3 by 7. So the number of rows is 3 and the number of columns is 7, right? Similarly, I can make this even more intense. Suppose 7 by 4, and if I run this, so you can see, right? So 7 rows, 4 columns is how you will say. And then this is for the first dimension, first element and the second element, and in each of these elements there are 3 more elements. So like this you can play around with it, right? So this is for zeros. Similarly you can create for ones as well, and again you can pass the shape. So if I pass just suppose 6, it will create a 1D array, right? Simple. Now if I pass multidimensional, suppose I want to generate something like 6 by 3 by 4, it will create 6 by 3 by 4, right? So 3 rows, 4 columns, and then 6 of such elements. Now np.zeros and np.ones is doing what? It is creating an array and then it is initializing all the elements to either zeros or ones. Now sometimes what might happen is we want to create an array, but we might be, say, calculating the values later, or we might overwrite each of these elements later. So it doesn't make sense that I want to have this overhead of initializing all the elements. So instead of doing that, what if I just create the array of a particular size and I just say that, okay, this is the array that you have to create, but you can put any values that are already there in that memory location. So that is what np.empty does. Now, a lot of people get confused between np.empty and np.random. We will see random later. But you can understand from the name itself, what random does is it is going to generate the random numbers for us and it is going to initialize the elements of the array to those random numbers. Here, it is not generating any random numbers. It is not initializing. What is happening over here? Let's read it. The function empty creates an array whose initial content is random and depends on the state of the memory. In very simple terms, whatever garbage value or whatever value was present in that particular memory that you are allocating for this array, it is going to be there. So it is not having the overhead of, say, initializing the elements with anything. So it is going to be faster than np.zeros, np.ones, np.random. So np.empty is going to be very fast. It is used very frequently whenever you have to just create an array and you know that anyway you're going to override all the elements later. So it's also a bit tricky because there can be random values that are present over there. So you should know that, okay, any garbage values can be present over there, right? So let's actually check it out. Again, rest everything is going to be same. So here also we can pass shape. So if I just pass 3, here you can see that there are 3 elements. And if I just give any other shape, like for example, 3, 8. So rest everything is same, right? The concept remains same. It can also be NA and the values can be null as well, right? Similarly, we can create more arrays. Now these are very, very useful, right? Now what is np.arange doing? You can also remember it like it is creating a range of values, okay? So this is another way of just remembering that you can use np.arange, but obviously you'll use this so much, you'll get used to it. np.arrange, np.linspace, both of them we have in fact used in our matplotlib video. So if you want to check that out, you can do that as well. That is for data visualization. So I was creating all of this data and then visualizing it in the plots, right? So we used np.arrange and np.linspace over there, and you'll be able to see that this is what is used in the documentation also in matplotlib, pandas. You will find this very frequently. So this is very, very common and very, very useful. So what it is doing over here is that we have to specify the first number, the last number, and the step size. So we have to start from 2. The last number is 9. So till less than 9, 9 is not inclusive, and this is the step size. So you can see it is starting from 2, then 2 plus 2, 4 plus 2, then 6 plus 2. Here, even if we gave 10, no, it would not come. So let me actually show it to you. Even if I give till 10, it is not going to come because it is not inclusive, right? Similarly, I can give for any step size. If I give 3, it is going to come like this. You get the point, right? You can also give something like 0.5. And if I print this, you can see that 0.5 is the step size. So 2, 2.5, 3, 3.5, and so on till 9.5. So 10 is not included. Linspace is slightly different. Just it mentions the number of elements that you want instead of the step size. So they both are essentially doing similar thing only. Here we give step size and here we give the number of elements, right? So it's kind of similar. And again, you can remember it like we give like, the number of elements that should be spaced out in that particular range. So you can remember the terms like this. So here the number of elements that you wanted is 5. So if I just give 5 also, it will understand that I want 5 elements. Similarly, if I want 10 elements, it is going to give me 10 elements. So this is nothing hard, right? Also, you can give the type that you want. Like by default, you can see that is mentioned that is np.float64. That is why you can see it is all coming in decimal, right? So if you want it as integer, you can do that as well. And this is true everywhere. You can do this. And if I print this, you will be able to see 1, 1 instead of this 1 dot 1 dot, right? So instead of decimals, it is doing this. I could also do the same thing for zeros as well. See, same thing. Coming to sorting and concatenating, as the name suggests, we'll be sorting and concatenating. So let's just copy this and okay, let me just sort it. So we can do np.sort. And if I pass our array into it, you will see the sorted array, right? But now there are a lot of additional functionalities that NumPy gives. Like for example, if we want an indirect sort, let me actually show it to you very simple terms. If I create an array, let me create a very simple small array, okay? And I'm going to create suppose 30, 10, 20. And now if I give argsort, okay, and np.argsort, what this is giving is indices in this array. When if you would sort this, like this is the index of those elements. Let me explain it. So the sorted would be 10, 20, 30, right? So 10 is present at what index? It is present at first index. 20 is present at what index? It is present at second index. 30 is present at what index? It is present at 0th index. So it is basically giving us indices, right? So you can use that for indirect sorting. There you can use something called lex sort, very similar, when you want to sort based on multiple keys. Like for example, you want to sort say based on the names as well as ages, right? So you can sort like that also. Search, sorted, partition. So this is like a lot of detailing. Obviously, if you are able to do all of this, this shouldn't be so hard, right? So I'm not going to be covering like that level of detailing. Partition sort, okay, let's just actually look at it. So if I do partition sort over here and I do np dot partition. Now if I give this array and give say 3, okay, and if I run this, what you will see is, okay, this entirely is sorted, but okay, let's take another example. Again, I took a random example and it is again coming sorted. Let's try more. Suppose I give this as 98. Okay, now it is not sorted, right? 98 and 90, you can see this is not sorted. So basically what happens over here is that the first 3 elements are going to be lesser and then these elements are going to be bigger. Now these don't have to be sorted within themselves. You can see 2312 is not sorted, right? 1243 is, but 23 is actually before. So it is just partitioning the data that, okay, these 3 elements are smaller than the rest of the elements. Which, if you know DSA, which algo do you think they would be using internally? It would be interesting to discuss, right? That is why basics of DSA very, very important. Let's see how many of you can answer this. Partition, simple partition, right? So you should be able to tell this. Similarly, if I give say 5 you will see that the first 5 elements, so 1, 2, 3, 4, 5, these will be lesser than these. Okay, so this is how partition works. So like this, you can play around with the documentation. Concat is again very simple to understand, right, from the term itself, that it just concatenates two arrays. So let me actually copy this as well. Sorry about that. Both the arrays got concatenated. Okay, so similarly, if we take more examples, suppose I have this. Now, if I concatenate this, here they have given something called axis equal to 0. What does that mean? See, axis equal to 0 meaning ki they are just basically vertically stacking over each other. So if you check the shape of this is what? It is 2 by 2. What is the shape of this? It is 1 by 2. If you don't believe me, actually let me just print it. Right, so if I print, if I print x dot shape and let's print y dot shape, and if I run this, you will see 2 by 2, 1 by 2, right? So the shapes have to be similar to stack on top of each other. So suppose over here the shape was not 1 by 2, okay? If it was 1 by 3, it is going to give us error. What is the error? That all the input array dimensions except for the concatenation axis must match exactly. So except the concatenation axis, meaning ki here we are vertically stacking on top of each other. So if you want to stack 3 also, if you want to stack 4 also, that is fine. But this number should be same over here, right? So suppose I try to stack one more array, right? So if I give another array, it is fine. So it is stacking vertically, right? So axis equal to 0 meaning it is going to stack vertically. But then again, this should be same, right? So that is one thing that you should remember while concatenation. Next in the documentation, they have again talked about shape and size a bit, but I hope now you are completely confident about number of dimensions, size, shape, so this should be fine. Let's move on to reshaping an array. From the name itself, it should be obvious, but let's check it out. So reshape will give you new shape to the array. So new shape to the array without changing the data. Now this is very, very important. So whatever was there in the original data, the same data is going to be present in the new array itself, right? So now let's move on to actually, let's check it out. So if I generate a new array, okay, if I do something like np.arange and let's pass on say 2 to 10 and suppose let's keep the step size as 2. Now how many elements are there in this array? There are 4 elements. Now what I can do is I can rearrange this. So I can do basically reshape and give that, suppose now the new shape that I want is 2 by 2. So I get 2, 4, 6, 8. You can see there are 2 rows and 3 columns, 2 rows and 2 columns. But now my question to you is that what if, okay, what if I try reshaping to 2 by 3? Then what would have happened? So if I did this, you can say cannot reshape an array of size 4 into shape 2 by 3. So they have explicitly mentioned in the documentation also that when you use the reshape method, the array you want to produce needs to have the same number of elements as the original array. Okay, so if you start with 12 elements in the new array also, there should be 12 elements. So let me actually just move this and let's take more examples. Suppose we want 6 elements. Okay, so let's generate suppose np.arange and let's have 6 elements, right? So suppose I have 1 to 7, right? And let's run this and let's see A has 1 to 6, right? So now what I'm going to do is I'm going to reshape it to say 2 by 3. So 2 rows and 3 columns. I can also reshape it to 3 by 2, which would be 3 rows and 2 columns, right? So like this, you can play around with it. Another thing to note over here in the example, they have done np.arange 6, right? So they have passed only one element over here, only one value, right? Over here, I passed 2 values. But when we understood arrays, I was always passing 3 values, start, stop, and step. So what exactly is happening over here? So always whenever you have such confusion, everything is present in the documentation itself, okay? It's not at all hard. You can see over here, start and step are under square brackets, right? And if you read about it a bit more, just go down and let's read about start, okay? Something, something, something. The default value of start is 0. And similarly, the default value of step is 1. So when I give just a single value, it takes this as the stop value, and that is also not inclusive. Again, if you have confusion, you can see the documentation. Here you can see there is a square bracket for start, but for stop there is no square bracket. So stop is not inclusive, right? That is when I do this, it comes from 0 to 5 and not from 0 to 6. If I want from 0 to 6, I would have to give 7, right? So I can, if I pass one value, it is going to take that as a stop. If I give two values, like where I just did right now, right, 1 to 7, it is going to take this as start and this as stop. If I pass three values, it is going to take start, stop and step. This you already know, right? So everything is there in the documentation. Don't freak out if you're not understanding anything, just go through the documentation. Now another thing, right now what I did was I did reshape something like this, right? A.reshape. We can also do something like np.reshape and pass A inside this. So let's try that as well. Suppose I assign this to array and let's print array, right? So let's do this. Now this is there in array. What I could also do is np.reshape and I can pass my array into it and I can give the new shape. So here you can see in np, okay, if I just pass it like this, here you will be able to see what all things I can pass, right? A, new shape and order. Okay, what is order? Let's check that out also. But suppose my new shape is, suppose 3 by 2. Okay, let's do this. So here you can say I have now 3 by 2. Now what is order? Let's check it out. So suppose if I try reshaping to, suppose I am reshaping this 3 by 2 to 2 by 3 and the order that I am giving now is suppose F. Okay, there can be many values of order. If you go down in the documentation, you will be able to see there is C that you can give, there is F that you can give, and they have explicitly mentioned what it means also. C like order, how it is going to be saved in the memory. F stands for fortin actually. So let me actually run this and show it to you. Now you will notice something very nice over here. So here if you notice, in one row the values are coming from the column. So 0, 2, 4, 1, 3, 5, right? So 0, 2, 4 came from this column and they were converted to this row. Again from this column they were converted to this row. Now suppose I just did this. Okay, this is my original array. This is my reshaped array. Now suppose I did reshape array and suppose 2 by 3 only. But my order is now C. Okay, there should be no confusion in the documentation, so that is why I am going to just put it over here as well. Now here you can see the values that were there was 0, 1, 2, 3, 4, 5. Can you notice the difference? See, this is the array that I am reshaping in both the cases, but here the values are 0, 2, 4, 1, 3, 5. Here the values are 0, 1, 2, 3, 4, 5. Because the order in which it is going through the array is different. One is going row wise, one is going column wise. So like this, there are a lot of customizations that are possible. A lot of detailings are possible. Sometimes you want to access the elements row wise, you want to work on them row wise. So you go ahead with that. Otherwise you can go column wise, right? So this is it. I think we can move ahead for now. But yes, I hope now you're feeling confident about arrange as well and about reshaping as well. Coming to adding a new axis to an array, I know you must be thinking that, Keerti, we were already adding a new dimension or a new axis to the arrays by reshaping them. And you are absolutely right. When we converted from 1 by 6 to 3 by 2 or to 2 by 3, we were essentially adding a new dimension or a new axis. But we were also restructuring the elements. We were restructuring from 1, 2, 3, 4, 5, 6 to 1, 2, 3, 4, 5, 6 or to 1, 2, 3, 4, 5, 6 like this, right? What if we do not want to restructure the elements, but we want to add an extra dimension? So for that, we can use np.newaxis or np.expandims. Both of them do the exactly same thing. And let's look at examples as well. So this is the array that is given. Let's take the same array. So here the shape is 6, right? And what is the number of dimensions? 1. Now if I add a new axis to it, so what am I doing? In A, I am doing np.newaxis. So I am adding a new axis, and when I do this, this is basically like a row vector, right? So what are the dimensions now? So now the number of dimensions is going to be 2. So if I check a.endem, it is basically 1. But if I check a2.endem, it is 2, right? So I have now converted from 1 dimension to 2 dimensions. I have added a new axis over here, and I have basically converted this to a row vector. I could also convert it to a column vector like this. So here what I'm doing is, here whatever the elements were there, I am adding a new axis like this, right? So I'm converting it to a column vector 6 by 1. And the exactly same thing can be done by np.expandims as well. So I can again convert it to a row vector or a column vector by giving the axis. So when I do expandims axis equal to 1, I again get a column vector. But when I do axis equal to 0, I get a row vector. So it is essentially the same thing. In expandims, we are mentioning the axis and converting into row vector or column vector. What is the difference between reshape and this expanding dimensions? Here we are not restructuring the elements, we are just adding a new dimension. This is more explicit, right? We are not making any changes to the structure of the elements that we already had. Coming to indexing and slicing, this works the same way as Python list, and we have also covered this in our pandas video, so it should be easy and clear. But let's do it still, right? So let me actually create it separately. So if I create an array, suppose np.array, let's take a different example, suppose something similar only, suppose 12, 89 and 45. Now what I'm going to do is, I can firstly access the elements like this. I can also slice them down. So basically what I'm going to do is, I'm going to access suppose just the last two elements. Okay, so what I can do is, I can do something like this, that array from suppose the first index till the end, right? So from the first index till the end. So similarly, suppose I want from the second index till the end, it will be the same thing, right? I'm getting from 45. So in this particular case, if I do this, I should get the same answer because this itself is the last element. If I try to access something like this, what should happen? I'll get an empty array because there is nothing at that index, right? So we can do this as well. Plus there is also negative indexing. So if I just do -2, I will get 89 because that is the last second element. If I do from -2 till the end, I'll get this. If I do suppose from the starting till say -2, then I'm going to get 12, right? And this is not inclusive. So if I do till -1, I'll get 12 and 89, right? So, yep. Great. So what this essentially means is that give me all the elements except the last element. So when we did colon -2, that meant give me all the elements except the last two elements, right? Now moving on to slicing, this is one way of slicing, that from this particular value to this particular value. We can also give conditions, right? So if I actually see this, okay, let me copy this particular array, and if I just do a less than 6 and I print it, so here I have a boolean array which is telling that for each of these indices, is this value true or false? So a less than 6 should be true for all of these values, right? So till here it is true, for all the other values it is false. Now when I do print a of a less than 5 or a less than 6, it will give me all the values which will have true as the answer. Okay, so if I just do a less than 6, then I will get all the values that are less than 6. And just see that it is not giving me in a new row or something. It's just filtering out those elements and it's giving me in a new array, right? So let me actually give a better example so that it is completely clear. Let me copy paste this. Just give me 1 sec. Now here let's take some random values. And now if I do a less than 5 or a less than 7, if I do this, now you can see that, see, it is false for this, then it is true for this, then again it is false for this, it is true for this, so there is a true. For 7 also it is false because it is not equal to, it is just less than, then it is true for this value, right? Now when I do a of a less than 7, it is going to give me all the values 3, 6 and 2. So out of all the elements that we have, give me all the values for which this condition is true. And it doesn't have to be a single condition, it can also be multiple conditions, it can be any condition whatsoever. Like for divisible by 2, they have given a mod 2 equal to 0, right? A greater than or equal to 5, is it greater than or equal to 5 as it suggests, right? So let's check this out as well. So suppose here itself, I want to do a less than 7 and whenever we give multiple conditions, if you remember the other videos, we have to put it in brackets, otherwise it is going to give us an error. So if I give a greater than suppose 74, and if I run this here, you can see there are no values which are less than 7 and greater than 74. And if I give or, Then let's do this. Now see 3, 75, 6, 84, 93, 2. Now which all values are not coming? See, because I've given greater than 74, I'm getting 75. If I change this to 75, obviously I'm not going to get 75. So I can use any operators. It can be or, it can be and, it can be anything. So far we have gotten the elements itself as the output, right? What if I want the indices as the output? So we can use something called np.non-zero. So don't get confused by the term. It is not like we are trying to find the non-zero elements. Here it basically gives us the indices of the array. Again, it can be a bit confusing, but with practice you'll get used to it. See, over here we can give any condition. So just this condition itself, if I have this in A, right? So I can do something like this. I can do np.non-zero and the same condition. Okay, let's give this condition itself. And if I run it, see here we are getting how many elements? 1, 2, 3, 4, 5, right? So here there are 5 elements only, but these are the indices across each dimensions. So 3 is present where? 3 is present at 0, 2, right? So this is the row index and this is the column index. So 3 is present at 0, 2, is that correct? 0, 2, yes. Then 6 is present at 1, 1. So 6 is present at 1, 1. 84 is present at 1, 3. Similarly, 93 is present at 2, 0 and 2 is present at 2, 2. So this is how it just returns as indices, rest everything is same. So if you want to print the list of the coordinates, this is how you can print it, right? You can just zip this and you can print that as well. But non-zero gives you indices. This is the difference. Now let's come to creating an array from existing data. See, slicing is one very simple way. So when we slice from 3 to 8, we are just taking like a sub part of the array, right? So from 4 to 8 and we are creating a new array from this. So we already have been creating new arrays from the existing data. So if you check all of these conditions, what are we getting in the return? We are getting a new array itself, right? So we are already doing this. We are creating an array from existing data. We just should check out horizontal stack, vertical stack, split, view and copy. Let's do this now. So this slicing we have already seen. For vertical stack, horizontal stack, see they have taken two arrays and they are just vertically stacking. So it just comes on top of the other. Horizontal stack adjacent to each other. Again, take care of the shape. It should be obviously, you should be able to stack it. That's common sense, right? So if I take this and if I try to stack something that is not of the same size, like for example, suppose over here there is 3 and suppose over here there is 4. And now if I try to stack it, what should I get? I'll get an error, right? So it will say all the input array dimensions except for the concatenation axis must match exactly. So now if I change it, or suppose for example, I add another over here, I will be able to stack now, correct? Similarly, horizontal stack also, make sure that the number of columns is same. Looking at edge split, this is again very interesting. Let's take this example. So in this particular code, what they have done is they have taken the numbers from 1 to 25. The step size by default is 1. So you're getting 1 to 25. So there are how many numbers? 25 is not inclusive, right? So there are 24 numbers. Now they are reshaping it to 2 by 12. So that is why 24 numbers, right? So 1 to 24. Now what we can do is split it. So here what they are doing is they are trying to split x and they are saying split it into 3 equal arrays. So if I copy this one and show it to you, they are splitting into 3 arrays. So till here there is one array 1, 2, 3, 4, 13, 14, 15, 16 is one array. 5, 6, 7, 8, 17, 18, 19, 20 is another array. So horizontally splitting it. So one split is happening over here, another split is happening over here. So here we are telling ki 3 equal arrays, but you can also tell ki split at these positions. So here they are telling ki split after the third and the fourth column. And not just after third, fourth, you can split anywhere. Like over here when I say split after third and fourth column, after the third one and after the fourth one. So this is one array, 1, 2, 3, 13, 14, 15. 4 and 16 is another array. Now suppose in this itself I added that may be split after 7th column also. So you can see there's another splitting after 7th column or even again after 8th column. So you can split into as many arrays as you want. So this is horizontal splitting. Another important concept is of views and copies. See, whenever you are splitting and creating new arrays, you are creating a shallow copy. Basically, both of them are still pointing to the same memory itself. So suppose, for example, let's take a simple array. Let's take suppose, okay, let's create only. I have this array, right? Now when I do b equal to array, I have both the arrays are same now. Now when I change the value of say b of 2 equal to suppose 10, and now I run this, if I try to print both of them now, you will see that both of them changed because there is a shallow copy. Both of them are essentially pointing to the same memory. Here I tried copying, but similarly if I tried by slicing also. So this is ARR, right? So if I want to print ARR, this is ARR, right? Now if suppose I slice ARR something like this from 2 to 4. Okay, and I print b, you can see that b is 2, 3, right? Now suppose I assign b of 1 is equal b of 1 is equal to say 20, and if I run this, now if I print ARR, you can see that 20 is now changed over here because b was what 2, 3, but it was essentially pointing to the same thing. So even when you're slicing and you think that you've created a new array, it is pointing to the same thing in the memory. So what are we doing essentially is we are creating views. Okay, so it is very, very important concept over here. So here it looks at the same data as the original data, shallow copy. Views are an important NumPy concept. NumPy functions as well as operations like indexing, slicing. So all of this, whatever we have done so far, indexing, slicing, is returning views whenever possible. This saves memory. Why? Because both of them are pointing to the same memory and is faster, right? So no copy of the data is made because it is pointing to the same thing. So it is obviously faster. So obviously whenever you modify data, make sure that you are aware of this, that the original data will also be changed. What if you want to create deep copy? What do you have to do? You have to do something called a.copy. So if I have array like this, and if I copy it like this, now if I make any change and I try to print, now you can see that the change 20 happened only in B and not in ARR. So whenever you want that the change should not get reflected in the original array, don't just assign, create a deep copy by doing dot copy. Very, very important concept. Coming to basic array operations, everything addition, subtraction, multiplication, division can be performed, and you already know this. All the operations are going to happen element wise. Why? The default mode in ND array is what? It will perform all the operations element wise, right? That is the default mode, and this happens because of the concept called broadcasting. So you already know what broadcasting is. It is saying, it is given to you that the dimensions of the array must be compatible. If the dimensions of both the arrays are not equal, or if the dimensions are not compatible, we will get a value error. So let's check it out. They have taken very simple examples. They have created two arrays, 1, 2 and 1, 1, and they are just adding, subtracting and all of that. Let's take some different examples. Suppose, for example, I am taking np.arange and I start from say 2 to 10. So I have not given steps. So by default, the step value will be 1, right? Similarly, let's take b also from 5. Now let's take some bigger number, okay? So now if I try printing a and b, what are the values? We can see that the number of elements in a and b are not same, right? So if I do a plus b, what am I getting? I'm getting a value error. Operands could not be broadcasted together with shapes 8 and 10. Right, so it will give you error. So if I have to add them, I have to make sure that the dimensions are compatible. Both of them have the same shape, right? So if there are 8 elements over here, there should also be 8 elements over here. So 5 plus 8, 13. So now they are compatible, and if I run this, now I'll get the array, right? So it doesn't look compatible because obviously there are double digits over here, it's all single digits, but you get the point. I can also do a minus b, I can also do a into b, so this will take care that the elements are multiplied element wise, right? So 2 into 5, 3 into 6, 4 into 7, like that. So 5 like 9 into 12 is 108. So you can see element wise it is multiplying. Similarly, A by B also I can do. So this is again element wise. So we have done addition, subtraction, multiplication, division and all of this. We can also perform sum. So if we want to get sum of all the elements in the array, we can just do this. So if I want to see A dot sum, if I just do this, I'll get sum of all the elements. So suppose if it is not clear from here, let's change the numbers from 1 to 10 and suppose another 1 to 10. Let me actually copy this instead of making change over here, because the code is available in the description, so you should not get confused. So here you can see that I am getting the sum as 45. So 1 to 9 sum is 45 only, right? So this is for all 1D arrays that we have seen. Suppose I had a 2D array and I also wanted to see sum of just the rows or of a particular column. I can do that as well. Of all the rows, I can do axis equal to 0. For all the columns, I can do axis equal to 1. For example, suppose this itself, I rearrange it, okay? Suppose I do a dot reshape to 3 by 3. So I have this now, and if I try to find the sum for axis equal to 0, I'll get the sum as 45. Here it has added all the elements over here and given us 45. Suppose I saved this in another variable and I did b dot sum, and let's run this. Let me actually just run this again and run this. Now you can see that I'm getting an array, right? Another way that you can actually do is when you are doing this reshape, right? So instead of doing it explicitly that you are assigning the reshape value, I can just do reshape like this as well. So if I do reshape 3 by 3, and now if I try to find sum, suppose a dot sum axis equal to 0, and if you want to see the value of a as well, let me actually just print it, print a. Now you can see that a value is this, and when we are doing axis equal to 0, that means we are trying to sum over the axis of rows, right? So 1 plus 4 plus 7, 5 plus 7 is 12, right? 7 plus 8 is 15. So similarly, if I want to sum for axis equal to 1, I'll get the sum across columns. So that will be 6, 15 and 24. So this is 6, 15 and 24. And you already understand broadcasting. Coming to some more useful operations that we can perform, min, max, sum. So we've already seen sum. We can also do min, max, mean, prod, std, right? So suppose, for example, I want to do max. Okay, so this will give me the maximum element in the entire 2D array. So this was our 2D array and this is the maximum of the entire of all the elements, right? Now suppose I do min, I'll get the minimum element. Now suppose max, min along rows, along columns, if I want that, I can do that as well. So if I do max along a particular axis, so if I do axis equal to 0, you will get 7, 8, 9, right? So among 1, 4, 7, max is 7, among 2, 8, 5, 8, the max is 8, like this. Similarly, if I do min for axis equal to 1, I should get 147. So in this, what is the minimum? 1. In this, what is the minimum? 4. In this, what is the minimum? 7. Obviously, I have taken 1, 2, 3, 4, 5, 6, and that is why you're getting the answers which are like adjacent to each other, but you get the point, right? Similarly, we can also find prod. So if I have to find prod for, say, axis equal to 0, we will be able to do that as well. 28, 80, 162. So 28, 80, 162, right? Similarly, for axis equal to 1, I will be able to get. Similarly for mean as well. So a dot mean axis is equal to 1. Suppose I do this. So here I've gotten the mean values as well, right? Similarly, if I do for suppose std axis equal to 0, I'll get it. Sorry about that. So instead of our axis, if I want to find std for the entire 2D array, I can do that as well. This is the standard deviation. So we have understood all of this. Creating matrices we have already seen. This is how you can find the max, min, sum. This is how you can add the arrays as well, right? So 2, 3, 4, 5, 6, 7. You can actually go through these examples and now you should be able to understand. We can also use something called random generator. So let's move to that, generating random numbers. So in a lot of places you must have seen something like this, np.random. Now you can also do rand, which will find as random values in a given shape, rand int, rand n, like this, right? So the most famous one is rand int that you must have seen, and here we can give from which value to which value. So this is like the range of the values and what is the shape of the array that you are going to get. Like for example, I say between 2 and 9 and the shape that I want is say 3 by 2. Okay, if I do this, you can see I'll get 3 by 2 and all the numbers are between 2 and 9. So this is how you can generate like random arrays. But now instead of rand int, there is a newer version which is like generating using random number generator. So if I copy this, fun fact, this is not going to work. So if you are getting confused, why is it not working? You can actually read more in the documentation, right? And if you look at the examples, you can see that they are using something called np.random.default.arange, right? So if I just add this at the top, and if I run now you'll be able to get, right? So this is essentially the same thing. We want the size as 2 by 4 and all the numbers should be within 5 range, right? So this is what we are getting. Similarly, now if I try getting for the same range and same size that we took, I'll get another 2D array, right? So 3 by 2 all between 2 and 9. So if you are getting stuck also, just go through the documentation, go through the different code examples that are given. It is not at all hard, right? So this is how you can generate random numbers with generator.integers. Now you can also find the unique items and counts by doing np.unique. I'm not writing code for this, is basic stuff, right? You're just finding the unique elements. If there are repeated elements, like there are multiple 11s, so you'll get only one 11, like this. You can find the unique values. You can also find the count of that. So all of this should be fine. Reshape we have seen in a lot of detail. You can also find transpose by doing dot transpose or dot t. So what is transpose? Your rows become column and your columns become row, right? So I hope you remember transpose from school days, right? Let's look at the transpose example. So here we can see that dot transpose, the earlier shape was 2 by 3, it got converted to 3 by 2, right? Let's take this example itself. So if we suppose save this in another array, and if I run this, this is our array, and if I do array dot t, see dot t is just short form, okay? So it's just doing transform is the same thing. I can also do transpose like this. So yep, and you can say I'm getting the same output. That means it is not changing the original array, right? So if I go back to array and if I do array dot transpose, and if I print array again, you will see that the array is unchanged. Where how many times I transpose, the array is unchanged, because transpose or transpose should actually get me back the original array, right? So even though I did it a couple of times, the array remained same, so it is not changing our original array. Little things like as you write code, you will understand these things. You can also flip your array or reverse your array, right? So this is like for 1D, it is very simple, right? 1 to 8 became 8 to 1. You can also reverse your 2D arrays, which basically will reverse along the rows as well as along the columns. So if you see over here, it was 1, 2, 3, 4, 5, 6, 7, 8 till 12. So your 12 became the of first element. So it went like this, 12, 11, 10, 9. So 12, 11, 10, 9. And then it became 8, 7, 6, 5, right? So 8, 7, 6, 5. So this is your now first element, and within that also the elements are obviously flipped or reversed. You can also reverse along a particular axis, like for example over the rows you can do with axis equal to 0. So here if you see, only the rows got flipped, right? And if you are not believing, let me actually just copy paste it. So if I have this array, okay, first thing to remember over here is, again when I am flipping, so this is my flipped array, my original arrays is still same. So when I do this, you can see the original arrays is still same. Now when I flip along the rows, okay, so this is flipping along the rows. So let me copy this. So you can see this flipped only along the rows, right? So 9, 10, 11, 12, 5, 6, 7, 8, 1, 2, 3, 4. So this did not flip. So here 12, 11, 10, 9 was coming. Here this did not flip, only the rows flipped. Similarly, if I wanted to flip only the columns, this is how we can flip only the columns. So here again see, this is your original array, right? So 4, 8, 12 became your first column, 3, 7, 11, then 2, 6, 10. So your rows did not flip, only columns flipped. So this is how you can control also that at which position do you want to flip. And you can also tell you want to flip this particular row or this particular column or from here to here. Just to explain the example, see here they are flipping the array to the 1. That means they are going to flip only the second row. So here they are flipping this. So earlier it was 5, 6, 7, 8. Now it is becoming 8, 7, 6, 5. And similarly, if you want to flip just the second column, you can give comma and say that I want to flip only the column. So only 2, 7, 10 got flipped, right? Rest everything is same. They are just flipping the second row or the second column. Coming to reshaping and flattening in multidimensional arrays. Now this is something that you will see so much, especially in end-to-end projects when you get started with ANNs and all of this. Neural networks, this is like very, very common. You will see this a lot. Just flatten and ravel. So what essentially happens over here is that if you have a multi-dimensional array, you are converting it into a 1D array. Okay, so you're just converting, like here there was 1, 2, 3, 4, 5, 6, 7, 8. So there were like 3 rows, right? It got converted to just 1D array, right? So this is how you can flatten. Now you might be thinking, what is the difference between flatten and ravel? Very nice, they have given it very nicely. The primary difference is that ravel changes the original array only, right? So this is basically a view, right? So whatever changes you make, it is basically pointing to the new array. This means that any changes to the new array will reflect the parent array as well. Since ravel does not create a copy, it's memory efficient. Flatten changes to your new array won't change the parent array, right? Because it is creating a new array altogether. So let's actually try it out. And if I do this, so now we can see that it got flattened. If I change this and print both the arrays, see this is the new array and this is the original array. So original array did not get changed, the new array got changed. Versus if we take the example for ravel and we do this, and now you can see that the original array also got changed. Coming to the final few things, so all the documentation that I have been showing you, right? So when I just show you np.max, I have been telling you that you can check out the documentation, right? Instead of doing that, you could also do something like this, help max, and you will get all the documentation. So they have just told that how you can go through documentation and all of that. Also working with mathematical formulae becomes very easy, as we have seen so far. So when we find mean square error, which is again very, very common, right? So in supervised learning and all, it is used a lot. So for that, you can just do np.sum, np.square. So mathematical operations are very, very easy using NumPy, and that is why the name NumPy, right? You can also save and load objects by doing .save, by doing .load. Now, .load text, .save text. Importing and exporting CSV, we have already seen this in Pandas. So I hope you have watched the Pandas video. It should be even easier to watch it now, because now that you know NumPy, I hope you all know that Pandas is built on top of NumPy, so it's very, very important to know NumPy basics, right? So check out the Pandas video. We have already seen all of this over there. Also plotting arrays with matplotlib, so check out the matplotlib video as well. We have again plotted a lot more complex graphs than all of this. We have plotted not just this, not just this, not just this, but a lot more. So check out that as well. But congratulations, so we actually went through the entire documentation. This brings us to the end of the video. If you have watched till here, I hope you really enjoyed it. I promise you there's so much more quality content coming up, and I promise you you're going to enjoy it a lot. I truly believe that this content deserves to reach more people. I am really working very, very hard for YouTube. So if you could please hit that subscribe button, you have no idea how much it would mean to me and will really motivate me to create a lot more content. So please do subscribe, share it with your friends, share it on LinkedIn. It would mean the world to me. And see you next time. A lot of content coming up. I promise that to you. See you next time. Bye.